Hey guys, we're doing this physics paper today. This is October-November 2022, 9702, paper 2, variant 3, paper 2, 3. Alright, so before we begin, let's take a look at the threshold. And this is the last paper 2 for the October-November series. I plan to do physics paper 4 afterwards, and chemistry, paper 4, followed by paper 5 and then some bio content. Hopefully I can upload all the videos before your May-June exams, May-June 2023. Let's see how it goes. So for variant 2-3, we had A at 34, B at 29, C at 24, D at 18, and E at 12. Alright, so out of 60, A was at 34. This was the lowest out of the three. B was at 29, C was at 24, D was at 18, and E was at 12. Although the mark for E was quite high though compared to the others, but A was the lowest, so the 80th percentile was a bit lower comparatively. So A star should be at around 40, maybe 40. Yeah, it should be at 40 or slightly higher. It's usually the halfway mark between full marks and 3-4. But A is extremely low here. For this specific variant, A is extremely low. So let's begin. Starting with question number 1. By the way, guys, if you don't know already, we've launched the official page for the YouTube channel. It's caiepapersolve.com. So here you have access to the past papers and videos. It's still work in progress, but yeah, you can check it out. So for example, if you wanna download this physics paper, this is October-November 2022. This is the grade threshold. This is the mark scheme. You have access to the question paper here, paper 2-3. Here you go. Threshold, mark scheme, question paper. So yeah, please check the page out. It's linked in the description. Anyway, let's begin. So the rate of flow Q of liquid along a narrow pipe of length L and radius R is given by this expression, where alpha is a constant. An experiment is carried out to determine the value of alpha. The data from the experiment are shown in table 1.1. Use the information in table 1.1 to show that the SI base unit of alpha is per second. Okay, let's do this. So we need to show that the SI base unit of alpha is per second. So let's make alpha the subject, that is Q times length divided by R to the power 4. Q has this unit of meter cube second to the power minus 1. Length is just meters. R is also just meters. So we end up with meter to the power 4 s minus 1 divided by meter to the power 4. We end up with just per second. That makes sense. There you go. Next, show that the percentage uncertainty in alpha is 15%. Okay. So percentage uncertainty of alpha is equal to percentage uncertainty of Q plus percentage uncertainty of L plus 4 times percentage uncertainty of R. This is mainly due to the power. R to the power 4 basically means R into R into R into R, which is why there's 4. So that's 3% plus 2% plus 4 times 4%. Sorry, I misread the values, my bad. L is 4% and R is 2%, so that's 4 times 2%, so that's 8 plus 4, 12 plus 3, which is 15%. That makes perfect sense. Next, Calculate alpha with its absolute uncertainty. Give your answer to an appropriate number of significant figures. So alpha is equal to Q times L, which is 2.72 times 10 to the power minus 8. Q times L, 2.5 into 10 to the power minus 2, divided by R to the power 4, which is 7.1 into 10 to the power minus 5 to the power 4. So that's 2.72 times 10 to the power minus 8 times 2.5 into 10 to the power minus 2 divided by 7.1 into 10 to the power minus 5 to the power 4. That gives you an answer of alpha is equal to, this is into 10 to the power 7, so 1 2 3 4 5 6 7, 2.6759 into 10 to the power 7. So we don't really know uh like how much we have to round it off to. This actually depends on the data, on the uncertainty actually. So let's find our uncertainty. We know that the percentage uncertainty of alpha is 15%. So can we write this, that 15 by 100 is actually equal to del alpha by alpha. So del alpha is equal to 15 by 100 times this value of 2.6759 into 10 to the power 7. Let's do that. Into 15 by 100. This gives you an answer of, try to match the power. Del alpha is equal to 0.4 1 2 3 4 5 6 7 into 10 to the power 7. So basically uncertainty, absolute uncertainty, can only take one SF. So this is it, and since I've matched the powers, this 0.4 actually corresponds to the first decimal place. The first decimal place, right? So I'm going to write my final answer as 2.7 plus minus 0.4 into 10 to the power 7. There you go. So alpha is equal to 2.7 plus minus 0.4 into 10 to the power 7. That's your final answer. Okay, that's all. Moving on to question number 2. There are 6 questions in total in this variant. The engine of a toy rocket pushes gases vertically downwards, and this results in the rocket accelerating vertically upwards from the ground. The rocket starts to move from rest at time 0. The variation with time t of the vertical velocity v of the rocket for the first 0.30 seconds of the flight is shown in figure 2.1. Okay. As the rocket moves, the thrust T provided by the rocket engine is 60 Newton. Assume that the mass of the rocket is constant for this part of its flight. Assume that air resistance is negligible. For this part of the rocket's flight, show that the acceleration of the rocket is 55 meters per second. We know that the gradient of the velocity time graph is basically the acceleration, right? So I'm going to pick 2 points. Ideally, the first and last point, 0, 0. And at point 3, it's this point, which is 16, 17. So that's 16.5 basically, right? It's 16.5, right? Yeah. So let's find out the acceleration using the gradient essentially. So A is equal to 16.5 minus 0 divided by 0.30 minus 0, which gives you a value of 55. That's all. You could also do it using V is equal to U plus AT. That's also fine. Same. All good. Next. State an expression for the resultant force F experienced by the rocket in terms of the thrust force and the weight of the rocket. Okay. So the thrust force is 60 Newton. So we know that the upward force is thrust and the down force is weight. So we know that F is equal to the upward force minus the down force weight. Because there's no air resistance, that is why this is it. Calculate the mass of the rocket. Okay, fine. So we know that F is equal to ma. and thrust minus weight is equal to ma. So the thrust force is 16, right? So 16 minus weight, which is mg basically, is equal to ma. So you can bring it on one side. Ma plus mg is equal to 16, or 55 plus 9.81, right? Was it 5.5 or 55? 55 is equal to 16. So ma is basically equal to 16 divided by 55 plus 9.81. So m is equal to 0.25 to 2sf, 0.25 kg. Great. At time t is equal to 0.30 seconds, a small piece of metal separates from the rocket. Calculate the height of the rocket above the ground at time 0.30. So the area under the graph of the velocity time graph is actually your displacement moved. So it's going to be half into 0.3 into 16.5. Height equals to area under the graph. Half into 0.30 into 16.5, which gives you a value of 2.475. So rounded off to 2.5 meters to two significant figures. But I'm going to use the exact value if we require it in the next part. The speed at which the piece of metal strikes the ground. Okay. So that metal over there, it basically, this is the main rocket, right? So a piece of metal just falls up, but this is moving at 16.5 meter per second. This is also moving at 16.5 meter per second. It's above this certain height of 2.5 meters. So what's it gonna do? The metal is gonna go slightly up and then just fall down. So what do they want us to find? The speed at which the metal strikes the ground. So our initial speed is u. We are moving at 16.5 because we were part of the rocket, right? And the equation that we use, I actually explained this in variant 2 too, so you can check that out if you guys want. There was a similar sum there. We're going to use the equation v square is equal to u square plus 2s. So I want to find my final speed. I'm considering the upward direction to be positive. Okay, and the gravity is directed towards the bottom, right? So it's going to be 16.5 square plus 2 into minus 9.81, since there's no resistance, and the distance, right? The distance is downwards, it's below us, so it's going to be minus 2.5. So that's basically v square is equal to 16.5 square plus 2 into 9.81 into 2.5. Okay, so I'm going to use my calculator answer, of course, from part 1 into 9.81 into 2 plus 16.5 square root over answer. I'm getting an answer of v is equal to 18 meters per second. 18 is my answer, and it matches with the mark scheme. Okay, moving on to question number 3. Hopefully we can wrap this up in 40 minutes. State the principle of moments. So principle of moments states that the sum of clockwise moments is equal to the sum of anticlockwise moments about the same point for an object in rotational equilibrium. About the same point for an object in rotational equilibrium. All right, see if that makes sense. So we have a hollow plastic sphere which is attached at one end of a bar. The sphere is partially submerged in water and the bar is attached to a fixed vertical support by a pivot P as shown in figure 3.1. The sphere has weight 0.30 Newton. The distance from P to the center of gravity of the sphere is 0.29 meters. Assume that the weight of the bar is negligible. Calculate the moment of the weight of the sphere about P. So a hollow plastic sphere is attached at one end of a bar. Fine, it's hollow. The sphere is partially submerged in water and the bar is attached to a fixed vertical support by a pivot P. Great. Assume that the weight of the bar is negligible. So this is the sphere. The weight acts like this, vertically downwards, 0.30. So if we draw this line over here, the line from the pivot, this angle is 40 degree basically. Now on the other hand, if I draw a line like this, so can I say that this weight has a component like this along the orange line, which is 0.30. Wait, I need to find that angle out specifically. So this was 40, which is why this was also 40. Now this is 90 degree, right? So this angle over here, this is going to be 50 degrees. So since this is 50 and this is 90 degree, this angle over here is 40 degree. Do you guys get the geometry? You do this in M1 quite often. Let me show you again. Check this triangle, okay? So this is a right angle triangle and this is 40 degree because this is also 40 corresponding angles. Now this angle is 90 degree, right? So this angle on the top over here is 50 degrees. 90 minus 40 is 50. Now this specific angle over here will be 40 degree. Why? Because you know, the whole thing is 90 and this small one is 50. 90 minus 50 is 40 degrees. See if that makes sense. That's the geometry. So essentially we just figured out that this angle over here is 40 degrees. Now 0.30 cos 40 is the component that is perpendicular to the pivot. We cannot take 0.30 cos sine 40 because it actually passes through the pivot itself. As a result, it will give no moment. So let's find out the moment of the weight of the sphere about P. That's 0.30 cos 40 times what's the distance? 0.29. 0.3 cos 40 times 0.29, which is 0.0666 or 0.067 to 2 SF. Okay. Now the system shown in figure 3.1 is part of a mechanism that controls the amount of water in a tank. Water enters the tank and causes the sphere to rise. Okay. This results in the bar becoming horizontal. So basically this pivot causes the ball to rise and overall the system becomes P basically descends and the system becomes horizontal. The system shown in figure 3.1 is part of a mechanism that controls this. Water enters the tank and causes the sphere to rise. This results in the bar becoming horizontal. Figure 3.2 shows the system in its new position. In this position, the rod R exerts a force to compress a horizontal spring that controls the water supply to the tank. R is positioned at the perpendicular distance of 0.017 meters above P. Okay. Now the variation of the force if applied to the spring with compression X is shown. So they're transitioning to Hooke's law basically after this question. Use figure 3.3 to calculate the spring constant. So we know that F is equal to Kx and K is equal to F by X and it passes through the origin. So let's write that down. K is equal to F by X. So We can take any point works. So what are we gonna opt for? I told you we usually take the last point, so that's 21, and the compression is basically it's being compressed, right? Yeah, 10 millimeter. So K is equal to 21 newtons divided by 10 millimeter, which is 10 into 10 to the power minus 3. Does that make sense? So we get a final value of 2100 Newton per meter. At the position shown in figure 3.2, the system is stationary and in equilibrium, right? The radius of the sphere is 0.0480 and 26% of the volume of the sphere is submerged. The density of the water is this much. Show that the upthrust of the sphere is 1.18. So how is this sphere in equilibrium? Check this. So the weight will now fully act downwards. It is a downward force, and the sphere actually experiences an upthrust, which is upwards, right? So these two values will actually cancel out, and only this section, the submerged portion, will cause the upthrust. Okay, so let's do this. We're going to use Archimedes principle, which states that upthrust is equal to V rho g. So let's find out volume. The volume that is submerged. Uh, that's basically 4 by 3 into pi r cube times 26%, right? So let's do this. 4 by 3 into pi, what's radius? What's the radius? It's 0.0480 pi r cube. So this into 26%. 26 by 100 times the density of the fluid that it's submerged in, which is water, 1.00 into 10 to the power 3, times g, which is 9.81. Let's do this. So 0.0480 cube times pi times 4 by 3 times 0.2626% times 1 into 10 power 3 times 9.81. This gives us a value of 1.18. Now here's the thing. Basically, all answers still now have been to 2SF, but check this data specifically. Here, everything specifically is given to 3 significant figures, which is why we also end up with a 3SF answer, which is 1.18 newtons. Now, by taking moments about P, determine the force exerted on the spring by the rod R. The force exerted on the spring by this rod R, by this specific rod, by taking moments, right? Okay. We are going to take moments about P. Okay, so P is our pivot. That's the technique we're going to apply. So here you go. Basically, the system is in equilibrium, right? They mentioned that it's stationary and in equilibrium. So what about this sphere on the left hand side? If we take P to be the pivot, right, we are experiencing a force of 1.18 upwards, right? So it's actually providing a clockwise moment. Now, I mentioned something wrong before. Check this out. The weight is 0.30, guys. Do you see that? The weight is 0.30. I assumed that the upthrust was going to be equal to weight, but it's not like that. The upthrust is actually 1.18. So they're not cancelling out, which means that there has to be another vertical force at the pivot. Okay, anyway, let's try to balance the moments. So upthrust is providing a clockwise moment, while weight is providing an anti-clockwise moment. That's the first thing. So what is the force actually providing over here? Check this. The force is actually compressing this spring over here. So clearly the force is applying, or the force is being applied in this direction, the force F. Now according to the pivot, right, the distance between this force and the pivot is actually 0.017 meters, and it's perpendicular, right? So it's actually providing one kind of clockwise movement. This is also providing clockwise movement. Those two clockwise movements are actually balancing out this anti-clockwise movement of the weight. This question was pretty hard to comprehend, but hopefully you guys understood that this force, this rod R, is compressing the spring. According to this pivot over here is 90 degrees to it, and we have the distance. Using that, we can actually find that out. Okay, see if you guys get it. Okay, P is our pivot. So let's do this. So what is the clockwise moment? What are the clockwise moments? Basically, the clockwise moments include, oh, I sorry, I misjudged it. I misinterpreted it in a bit. Upthrust is actually greater than weight, right? So the clockwise moment is greater than the anti-clockwise moment. So I misinterpreted the direction of the force. In this position, the rod R exerts a force to compress the horizontal spring. R is positioned at the perpendicular distance of 0.017 meters above P. The problem with this diagram is they don't show how the string is being compressed, right? But essentially, we just have to figure out that, um, you know, this is 1.18 and this is 0.30. So this one is providing an anti-clockwise moment, this is providing clockwise, but the clockwise moment is greater than the anti-clockwise moment. So we need an extra anti-clockwise moment to balance things out. So the force applied should actually be in this direction. But in the figure, it seems like R is applying a force towards the right. But somehow it's contributing to this, somehow it's contributing to the anti-clockwise moment, apparently. Because if you think of it this way, right? If you apply a force like this, it will rotate like this, right? This is clockwise. Anyway, whatever. So basically, since the value of upthrust is greater, this force needs to support weight, right? So let's do that. So I'm taking the anticlockwise moment, which is 0.30 times this distance over here, 0.29. And we are going to add that force F with its perpendicular distance 0.017. And this is going to balance out the clockwise moment of 1.18 times 0.29. Let's solve this. 1.18 times 0.29 minus 0.3 times 0.29 divided by 0.017. This gives you an answer of 15. The two significant figures, since our data has a minimum of 2 SF. So see if you guys get this, and if you do have queries, please comment below. Um, the system shown in figure 3.1 is a part of a mechanism that controls the amount of water in a tank. Okay, fine. Maybe somehow it's applying a force in this direction. But basically, yeah, you could do the math by seeing these values, by making it match. Clearly upthrust is greater than weight, so this force F needs to support the weight itself, right, to balance things out. Anyway, let's move on to the next part. Calculate the elastic potential energy of the compressed spring. Fine. We know that elastic potential energy is half kx square or half fx. We have the spring constant. It happens to be 2100. We also have the compression, which happens to be. Oh, we don't have the compression really, but we can find it out from the graph. How? Check this. We know that the value was 15.0, right? So you can read it off from the graph itself. 15 corresponds to a value of, let's see, it's basically a bit more than 7. It's between 7 and 7.2. It's basically something like 7.1. Okay, but if you guys want, since we can't accurately read it, we can just do this. F is equal to kx, so x is equal to F by k. So the force was 15 while k was 2100, right? There you go. Wait one sec. So that gives a value of x is equal to 7.15 times 10 to the power minus 3 meters. Okay, so half kx squared, that's 7.15 into 10 power minus 3 whole square. This gives you an answer of 0.054 if you round it off, 0.054 joules. This is one way to do it, right? Or you could just do half fx, half into 15 times 15 by 2100. That works as well. Okay, everything's fine. Same thing. So when the sphere moves from the position shown in figure 3.1 to the position shown in figure 3.2, the upthrust on the sphere does work. Assume that the resistive forces are negligible. Explain why the work done by the upthrust is not equal to the gain in elastic potential energy. Basically, guys, check this. The As the sphere is submerged further, the upthrust increases, and it does work to, basically this thing, it's getting submerged deeper, and as a result, this upthrust is doing some work, and it is eventually making the rod completely horizontal. Okay, because there's a force that the object sphere feels, the upthrust, due to it being submerged. Now, here's the thing. Why doesn't why isn't this the work done by the upthrust equal to the you know elastic potential energy of the spring? Because there are no resistive forces, right? So all work done by the upthrust is supposed to be converted to elastic potential energy gained by the spring. The logic is the water has increased, right? You guys have to understand that water actually increases in the system. As a result, the ball actually gains some height. So, uh, some of the work done by the upthrust is actually also like the ball also gains some gravitational potential energy as well. Okay, so check this: the work done by the upthrust as well as the work done by the upthrust contributes to two things: the gain in GP as well as the gain in elastic potential energy. Does that make sense? Because the water level has increased, right? Because the water enters the tank and causes the sphere to rise. Does this make sense? The sphere was initially at this level, but now look, the sphere is at a higher level. right? The sphere was initially here, but now it's higher. You guys get what happened? Water level has increased like this. The water has increased, so the sphere has also come up. So it has gained some GP. So how did this happen? The upthrust basically did some work. Okay, does that make sense? Fine. Okay, so how do we word this? The sphere has gained gravitational potential energy. Fine. So not only does the upthrust do work to increase the elastic potential energy of the spring, it also causes an increase in the gravitational potential energy. So if they asked you which one is greater, the work done by upthrust or gain in elastic potential energy, your answer would be the work done by upthrust, because it is also contributing to an increase in GPE of the sphere. This was a complicated sum, honestly. Compared to the other three variants, this was the hardest one, probably. This is the hardest question in all three variants. So yeah, please read this properly. This is not that simple or straightforward. You had to apply your knowledge. Anyway, moving on. We have three questions left, 4, 5, and 6. Won't take long. A progressive longitudinal wave travels through a medium from left to right. Figure 4.1 shows the positions of some of the particles of the medium at time t naught, and a graph showing the particle displacements at the same time t naught. Okay. So it's a longitudinal wave. We know that there are compressions and rarefactions. Particle displacements to the right of the equilibrium positions are shown as positive on the graph, and particle displacements to the left are shown as negative on the graph. So basically what they mean by this is, you know that a longitudinal wave vibrates like this. The energy is propagated in this way and the vibration is like this. So essentially what they mean is, there was an MCQ like this recently in the ON22 paper. Like here the displacements to the right are shown like this basically, and displacements to the left are shown like this. So where is the demarcation actually? After each x, y, and z, the demarcations can be made between moving left and right. Here again we are moving to the right with maximum displacement, followed by we are moving to the left with minimum, then maximum over here, then it gets smaller. Okay, so this is the diagram. Now on figure 4.1, draw circles and two particles which are exactly one wavelength apart. Okay, so let's see which ones. Basically you can do it like this. This particle, okay, is in phase with this one over here. So how many particles are in between? 1, 2, 3, 4, 5, 6, 7. So this was one possibility that you could do. You could also circle these two, this one and this one, but always the gap of 7 particles in between must be maintained. Okay, does that make sense? Clear? You could also circle these two, this one and this one. All right, so I'm gonna opt for these two. All right, but the gap of 7 particles must be fixed between them. Next, on figure 4.1, sketch a line on the graph to represent the displacement of the particles for the longitudinal wave at time of t naught plus t by 4. Interesting sum. So we know what happens after t by 4 seconds, right? Basically, the wave will move 1/4 to the left. So this point over here will move here 90 degrees, and this point will move here 90 degrees, this point will move here, this point will move here. Basically every particle will just move 90 degree to the right hand side. So we have to draw a curve like this, which has moved 90 degrees. Wait, let me draw all the points, it will be easier. Yep, here you go. Wait. There you go. And yeah, how do we draw this part? It should be over here. Here you go, like this. Okay, so this is our new curve. It has initial negative displacement and the amplitude cannot change. Okay, and it's just gonna move 90 degrees or 1/4 to the right. State the direction of motion of particle z at time t naught plus t by 4. Okay, so look at particle z, this particle over here. Now you remember what this the text told us? Particle displacements to the right of the equilibrium positions are shown as positive. So if you correlate z with this point over here, since we have a positive displacement, z is moving to the right. See if that makes sense. To the right. Or you could just say rightwards, because at this moment t naught plus t by 4, I can see that z has a positive displacement. On the other hand, something like y has a negative displacement, so it's moving to the left. Does that make sense, guys? The frequency of the wave is 16 kilohertz. The distance between x and y is 0.19. So x to y, guys, x to y is actually half, right? Half a wavelength. So we can say that half a wavelength is equal to 0.19. So lambda is equal to 2 times 0.19, which is 0.38. Great. Now we know that v is equal to f lambda, which is going to be equal to 16 kilohertz times 0.38, which gives you 6080 or 6100 meter per second rounded off. Fine. Next, longitudinal wave is traveling through a solid. The initial intensity of the wave is I naught. The frequency of the wave remains constant and the amplitude falls to half of its original value. Okay. Determine in terms of intensity the final intensity of the wave. Okay. We know that intensity is proportional to amplitude square. So can we write this? Intensity 1 by amplitude 1 square is equal to intensity 2 by amplitude 2 square. Now let's input the values. The original intensity is I naught and the amplitude is A, and the new intensity we do not know, right? But the new amplitude is half of its original, so that's A by 2 whole square. So we can write that I2 is equal to A by 2 whole square is basically A square by 4. So A square by 4 times I naught by A square. So we can get rid of the A squares. So we ultimately end up with I2 is equal to 1 by 4 I naught. So you have to write 0.25 I naught here, by the way. No fractions allowed. The sound wave in C now meets another sound wave traveling in opposite direction. State a condition necessary for these two waves to form a stationary wave. They need the same frequency, right? Or same wavelength. Or same period. Anyone works. State two ways in which a stationary wave differs from a progressive wave. So guys, mainly remember that stationary waves do not actually transfer energy. It has nodes and antinodes, okay? And adjacent particles are in phase given that they're within the same loop for stationary wave. But in a progressive wave, adjacent particles are not in phase. So let's begin. Firstly, a stationary wave has nodes and antinodes, which means that amplitude, remember that for a progressive wave, amplitude is constant throughout the whole wave. But for a stationary wave, amplitude varies in different points of the wave, okay? So a stationary wave has nodes or antinodes, and a progressive wave does not. Fine. What about the next point? Basically, a stationary wave does not propagate energy. Fine. It does not propagate or transfer energy. Okay. And a progressive wave does transfer energy, right? Transfers or propagates energy. Fine. Now, I was saying that, basically, different points on a stationary wave have different amplitudes. Fine. Different points on a stationary wave have different amplitudes. But on a progressive wave, like different particles may have different displacements, but all of them have the same amplitude. But in a stationary wave, we have nodes which have zero amplitude, we have antinodes which have maximum amplitude, and so on. Last one, I was saying that in a stationary wave, check this. These 2 points, right, A and B, they are adjacent to each other. Since they're within the same loop and they both just oscillate downwards, so they are actually in phase. So in a stationary wave, adjacent particles are in phase. So a stationary wave has adjacent particles that are in phase, and adjacent particles on progressive wave are out of phase, okay? And in a progressive wave, all points have the same amplitude or constant amplitude. Hopefully I could clarify. These are the 4 points that you need to learn properly, okay? Moving on, we have 2 questions left, question 5 and question 6. Let's wrap this up. State Kirchhoff's second law. So Kirchhoff's second law states that the sum of EMFs is equal to the sum of potential differences, or you could say the algebraic sum of EMF and PD is 0. Alternate way. And the second point is around a loop or around a closed circuit. Is that fine? So what do we have here? 3 identical cells, each of EMF 15 and internal resistance 590 milliohms, are connected in parallel across a conductor as shown. That's good. So we know that when cells are connected in parallel, the EMF is not added up sadly. Okay, the EMF is not added up sadly, although the currents will be added up according to Kirchhoff's first law. So the resistance of the conductor is 2 ohm. The total resistance of the circuit is 2.2. So basically you can think of these three these three internal resistors as being connected in parallel. These three resistors, inter resistors, are connected in parallel. And yeah, so how do we find out the total resistance of the internal resistors? The total resistance of the internal resistors is equal to 1 divided by 0.59 plus 1 divided by 0.59 plus 1 divided by 0.59, like this. So if you do that, 1 by 0.59 into 3 reciprocal gives you an answer of RT is equal to 0.197. Okay, so essentially it's a circuit like this. I combine the three batteries, okay, to give RT as 0.197. This is our combined effort. The EMF will still remain 1.5, and this is the conductor. Okay, it's something like this. Fine. Now what do we need to find out? Show that the resistance of this conductor is 2. Now these internal resistors as a whole, they are in series with the conductor AB, the two cylindrical sections, the one with two cylindrical sections. So they're in series, right? So total resistance is RT plus resistance of the conductor, right? So how do we find that out? It's going to be equal to the total one, 2.2, minus this 0.197. 2.2 minus answer gives you a value of 2.0. See if that's fine. So you guys have to understand that these three are in parallel. Okay, these three are in parallel, but overall they are in series with this conductor below. Okay, how did I figure that out? By looking at the junctions. I know that these guys are within junctions, right? So that means they are in parallel, because they told you three identical cells are connected in parallel across a conductor. So the conductor is in series with them. Okay, calculate the current in the conductor. Fine. So what's the total EMF? It is not 4.5, it's 1.5. Okay, it's 1.5. So the current in the conductor, we want to find out the total current, I. So how do I do that? V is equal to IR. I is equal to total EMF, which is 1.5, divided by the total resistance in the circuit, 2.2. So 1.5 by 2.2 gives us an answer of 0.68. Now here's the thing, there was another technique to find out the resistance of the conductor in part 1, but then you had to find out the current beforehand, which you had to do in part 2, which is why I don't prefer that, honestly. There you had to find out the current first and then divide the current by 3, because it's being split into 3 equal parts in the upper ones, and then apply Kirchhoff's second law, stating that E is equal to IR plus IR plus IR plus IR, like that. Okay, it's a bit complicated. You guys don't need to do that. E is equal to IR plus IR, essentially. Do you guys want to see the second method to do this? So you find out current, which is 1.5 by 2.2, which is 0.68. Now 0.68 is the current through here, right? But over here, current is split into 3 equal parts as 0.68 divided by 3, okay, because they're identical. Now we can apply Kirchhoff's second law. We can write that 1.5 is equal to IR, which is 0.68 times capital R. This is R, plus 0.68 by 3 into 0.59. You don't consider it thrice because they're connected in parallel, right? So if you do solve this, you're gonna get R as 2 as well, okay? But I don't prefer that. Now, the two cylindrical sections A and B of the conductor are made from the same material and have the same length. Okay, rho is the same, L is the same. We know that R is equal to rho L by A. The diameter of the section A is 4.3 and the diameter of section B is 7.6. The resistance of A is RA and this. Okay, so rho and L are the same. Fine. So let's try doing this. You get 1 mark for stating this. And then you can say R is equal to rho L by pi d square, right? Pi d square by 4, or R is equal to 4 rho L. R is equal to 4 rho L by pi d square. This is the formula. Now rho and L are the same. So RA by RB is equal to, we can also get rid of the 4 by the way, right? So 4 rho L, we can get rid of those. We can also get rid of pi, right? So that's 1 by dA square divided by 1 by dB square. So after reciprocal, it's actually dB square divided by dA square, which ends up being 7.6 square divided by 4.3 square. It is 3.12. To 2SF it's 3.1. Great. Next one. Calculate the ratio of drift speed. So we know that I is equal to NFEQ and drift speed is equal to V is equal to I divided by NAQ. Explain your reasoning, yeah? So drift speed of A divided by drift speed of B is equal to I divided by NAQ divided by I divided by NAQ. Now here's the thing, it's a series circuit, right? So we can get rid of I. Okay, what's same exactly? Guys, what is the same? Current is same because series circuit. N is the same because it's made of the same material. And Q is always the same, it's the elementary charge. Okay, so I, N and Q are same or equal. So we can get rid of those, right? So the only thing that we end up with is like this: VA by VB is equal to 1 by area of A divided by 1 by area of B, which is equal to area of B divided by area of A. Now, isn't that exactly what we did over here, kind of? Because check this: VA by VB. What is area? Area is essentially pi d squared by 4, right? Since it's a circle. So area was uh, pi dB square by 4 divided by pi dA square by 4. So we could get rid of pi as well and 4. So VA by VB is essentially dB square by dA square, which is the same as our answer in 1 because it was also dB square by dA square. So I'm going to opt for 3.1 here as well. Okay, so yeah, this was complicated in the sense that you had to figure these things out. Okay. Anyway, there was also other ways to solve part 2 which I don't prefer. You can check that in the mark scheme, but I wouldn't honestly recommend those. Do you guys get that? They're much more complicated and more time consuming. This is the easiest way to do it because we know the total current as, you know, it's the total voltage 1.5, the total voltage in the circuit divided by the total current in the circuit. Sorry, total voltage divided by total resistance in the circuit. That's the easiest way. The other way was if you found out the individual voltage that this conductor got, okay, which was yeah, you could find that out and then you could divide it using its resistance. Too complicated, you don't need it. Moving on to the last part of this question. The circuit of figure 5.1 is altered by removing one of the cells. State and explain the effect, if any, of this change on the potential difference across the conductor. Okay, so what do we have now? Same setup, it's just that instead of 2 we have 1. Sorry, instead of 3 we have 2. Fine, this is the setup currently. We have the weird setup. Who came up with this question, honestly? It's so annoying. Okay, so in general, this is still a parallel circuit. The net EMF of the battery is still going to be 1.5. It's not going to be added up. But let's take a look at the internal resistors. They still have 590 milliohm, right? 590 milliohm each. So 1 by RT is going to be equal to 1 by 0.59 plus 1 by 0.59. Let's check this. 1 by 0.59 into 2 reciprocal gives you an answer of 0.295. So beforehand it was a 0.197. Now it's 0.295. So what just happened over here? The total resistance of the circuit. You know the combined circuit I drew? Something like this. This is the combined one RT, the one in series. Now the combined resistance has actually increased. This is still 2, right? So what happens to the net current? Current in the circuit will decrease. The current over here will decrease. So its voltage will also decrease. Okay, that's the logic. So let's write this down. The combined internal resistance, important sum of the cells, will be greater. Or you could say that, the total circuit, the total resistance of the circuit, the total resistance of the circuit is greater because you removed a parallel component. Now, what do we have? There will be more lost volts, right? Or internal resistance takes up a greater share of the total EMF. Or the current in the total current decreases. I would write that personally. This is the last line. You could say that the current in the conductor or total current decreases. Okay, you could mention this point, or you could say that there are more lost volts inside its cell, or the internal resistance takes a greater share of the total PD. So what's the last point? What's our last point? Basically, so potential difference across conductor decreases. So let me repeat this whole thing, okay? So basically the total resistance of the circuit is greater now. So the current in the circuit decreases. As a result, we know that V is equal to IR, so PD across the conductor decreases. That's it. If you wrote that, you'll get full marks, okay? But yeah, overall, this was a hard sum as well. So comparatively, question 5 and 3 were hard, right? And the first part of 4 isn't everyone's cup of tea. Maybe you wouldn't be able to get it right on the first time around. Okay, so yeah, I get why the threshold was as low as it is, honestly. There's logic behind it. I just wanted to check this graph one more time. The Marxium said the curve has initial negative displacement, fine, and initial amplitude same as the original curve, okay. Curve has same amplitude as the original curve throughout. Curve has same wavelength as original curve throughout with constant non-zero phase difference. Yeah, this is fine. Okay, anyway, moving on to the last question for the day. Question number 6. Hopefully it's over soon. The nuclide carbon 614 is unstable and undergoes beta minus decay, emitting a high energy electron. So we know that electron has no mass, but it has a charge of -1, and it emits an electron antineutrino. And the compound, the new nuclear X that is created, has the same mass but greater charge, because 7 minus 1 is 6, and we need to balance the charge, the total charge. State the equation of beta decay in terms of fundamental particles involved. So basically we got an extra proton, right? Here we had 6 protons and 8 neutrons, but here we have 7 protons and 14 minus 7, 7 neutrons. So essentially 1 neutron decomposed to form 1 proton. 1 neutron decomposed to form 1 proton. So let's do that. 1 neutron to 1 proton. A neutron is basically UDD. It was converted to UUD, right? So in terms of fundamental particles, one quark, one down quark disintegrated to form an up quark, a high speed electron, and an electron antineutrino. Or you could say UDD was converted to UUD plus electron antineutrino. Okay, very important. Use the equation to show how charge is conserved in beta minus decay. Let's do this. Okay, so using the first equation, the one on the left, you know the down quark, right? It has a charge of minus 1 by 3e. On the right hand side, this up quark has a charge of plus 2 by 3e. The electron has a charge of minus 1, and neutrinos and antineutrinos have a charge of 0. So if you do the math, minus 1 by 3e is equal to plus 2 by 3 e minus 1 by minus 1e, which is minus 1 by 3. Okay, makes sense? It's conserved. Or on this side, it was plus 2 by 3 minus 1 by 3 minus 1 by 3 is equal to plus 2 by 3 plus 2 by 3 minus 1 by 3 minus 1 plus 0. So this one in total is 0, and on this side, try it. 2 by 3 plus 2 by 3 minus 1 by 3 minus 1, it's also 0. Okay, see, it matches. This is the first time I've seen this question, by the way. Neutrons were first proposed to exist more than 20 years before they were directly detected. In order to explain a particular experimental observation about beta decay, state an observation about beta decay that is explained by the existence of neutrons. Okay, so the interesting fact and the difference between alpha decay and beta decay is that alpha particles always have discrete energy levels, it's always fixed, but beta particles always have a range of kinetic energy. Why? Because the kinetic energy is actually shared between these particles. If this guy gets high energy, this one gets low. If this one gets low energy, this one gets high. So we never see fixed energies for the beta particles. Rather, they always have a continuous range. It's like a normal distribution. You'll learn this more in A2 when you study X-rays. So basically, the electrons or the beta particles emitted from the nucleus have a continuous range of, or it has different kinetic energies. Essentially, it's never the same. Why though? Like why is it so unstable? Like, why does it have high k sometimes and low k sometimes? Because the emitted neutrinos, the antineutrino or the just the neutrino, the emitted neutrinos take varying amounts of the same total energy released in the decay. So think of it like kind of like loss volts and terminal PD. Basically, you know that loss volts plus terminal PD must be equal to the EMF, right? So these neutrinos, the energy that they take plus the energy that is emitted by the beta, those two added up will be equal to the EMF of will be equal to the energy released in the decay. Now this is never fixed. Okay, it always keeps on changing. It depends on uh, number of facts. But an alpha particle always has fixed energy because nothing else is emitted along with the alpha particle. Okay, so yeah, this question has come in the past, but this is the most in-depth answer that they've wanted till now, so you should learn this for your exam. Okay, all right guys, we are done with this paper. Comparatively, this paper was much harder than paper 2.1 and 2.2. So yeah, you should do this paper very seriously. May June 2023 might be a hard one, so good luck with that. All right, so I'm going to link the paper for October November 2022 paper 2.2 up here, and the paper for October November 2022 variant 2.1 down here. And I'm gonna link the playlist for physics paper 2 up here, and hit the subscribe button. It would help me a lot. See you guys.